Hi everyone. Today we are going to expand on our understanding of the lifetime of large stars and look into neutron stars and black holes. So, today we're going to go over pulsars, the formation of neutron stars and black holes. We'll compare and contrast the formation of each. Why do some become neutron stars, some become black holes? We're going to look at binary systems, as well as some evidence for black holes, and then looking at some pictures of black holes. I should say picture in quotes there. So, brief review, remember that there's two pathways for the lifetime of a star, two paths that a star can take from a nebula, and it's dependent on their size. So, low to medium mass stars, which would include our sun, become a main sequence star. Once they run out of fuel, they become a red giant, then a planetary nebula into a white dwarf. Larger stars become higher mass main sequence stars, then to the red supergiant, a supernova explosion, and then depending on the mass, the star will either become a neutron star, or if it's extremely large, will become a black hole. So remember that small star death ends in a white dwarf. So a dead, smaller star is going to be a white dwarf. It is when all the fuel within the core of the star is used up, all of that hydrogen and helium. Remember, with the smaller star, it can only fuse hydrogen and helium. The smaller stars don't get warm enough to fuse any of the other heavier materials within the core. So at that point, once the hydrogen and then the helium is all used up, the star is officially dead. It will then become a white dwarf. Large stars, on the other hand, can become neutron stars or black holes. So a high mass star is going to become a neutron star after the supernova explosion. In order to create a black hole, it has to be a very, very, very high mass star. So only the largest, most massive stars will become black holes. So when we think about our supernova, remember here we have our supernova explosion. There's two types of supernova. And the supernova is when the star has a degenerate core and it collapses inwards. It ends up with that supernova explosion. So supernovas have two types. The type 1 is when there's no hydrogen spectral lines on the spectrum of the supernova. Type 2 is when there are plenty of hydrogen spectral lines. So that's the difference between type 1 and type 2. Does it have hydrogen spectral lines or not? So type 2 does produce those hydrogen lines. So we see type 1 in blue, type 2 is in orange, reddish, and we can see that there are type 2 has hydrogen spectral lines and a little bit of a different shape here when we're looking at magnitudes. So a neutron star is what is left behind by a type 2 supernova. So when you have a type 2 supernova, it has hydrogen spectral lines. It is going to be very, very, very dense, what is left over. So after that explosion, what's left as the remnants of the core of this star, it's going to be incredibly dense. Remember that it was degenerate material. And it's going to be spinning very rapidly, hundreds of thousands of times per second. The neutron star, what is left behind, is going to be almost as hot as the center of our sun, and it has an incredible magnetic field. So the magnetic field of a neutron star is about 1 trillion times stronger than the magnetic field of Earth. So neutron stars are a little interesting because in theory and the math and the physics of a neutron star makes complete sense, but we don't really know where any of them are. So physicists and astronomers are pretty sure neutron stars exist. In 1932, we had the discovery of the neutron, and in 1934, there was a paper published that explained the concept of a neutron star. So in terms of the math and the physics and the science, the quantum mechanics really behind the concept of a neutron star, it makes sense. It could be possible. So physically, it is possible for a neutron star to exist. Neutrons themselves spin very similarly to electrons. When they're dense enough, they become degenerate. And even when it is even more dense, this could actually support itself. The neutron could support itself by the pressure of the degenerate neutron. So it's a little bit similar to the setup of a white dwarf. It's going to be way hotter. So neutron stars form from a supernova. The supernova, the core collapses inward. If it is small enough, it's going to become just a white dwarf. If it is large enough, the pressure of those degenerate electrons in the core will not be strong enough to balance the weight of the entire star, the weight of all of that material. Say it's 8 to 10 or more solar masses. So what happens is the collapsing inward of this supernova initial collapse is going to continue, and the nuclei are going to be broken apart by gamma rays. So gamma rays are actually going to blast these different atoms into pieces. So we'll have electrons, protons just floating around, not attached to the atoms that they originally started with. Their atoms are actually broken apart. So that leaves electrons and protons sort of free flowing. So these freed protons combine with electrons and create a neutron, or it's also called, you can think of it as neutrino. Again, for our concept, think that they're the same. So the burst of neutrinos that are formed as this collapse continues, this creation of the neutrinos is actually going to help blast the outer layer of the star, I should say layers of the star, including the outer layers of that supernova, away from the core. So all that's left behind is the remnants of that core, which is what we call the neutron star. So this reaction is a huge collapse. If the star is big enough, it's going to continue collapsing, the supernova explosion. There will be gamma rays that break apart the atoms. The atoms will then reform, creating these neutrons. That formation actually will help to blast everything else out of the way. So all that we're left with in this region is that the remnants, what once was the core, which we now call the neutron star. So the core is generally at this point, less than 3 solar masses. So it'll be less than 3 times the size of our sun. So scientists are pretty sure that neutron stars are incredibly hot and spin very, very, very rapidly and have very strong magnetic fields. So as gases fall inwards, the object speeds up and warms up because it's being compressed. So these neutron stars are very, very, very hot, and they over time are going to cool off. They cool quite rapidly at first, but as they get smaller, there's less surface area. So they will cool slower and slower and slower as the neutron star continues to get smaller and smaller. The magnetic field comes from the magnetic field of what once was the star. So it's that same magnetic field around what used to be a massive star. It's all squeezed down to now this tiny little neutron star that's left over. The magnetic field becomes incredibly strong for such a small object. So can we observe these neutron stars? Not quite. Very, very, very difficult. They are incredibly hot. So all the radiation that's emitted is either in the gamma ray or the X-ray. Definitely no visible wavelengths. They're also very small. So remember, a star the size of our sun, or even 3 times the size of our sun, that's not something very bright. It's not, that brightness is not going to be something that we actually see in the sky with our eye. A neutron star is going to be something that, if we could see it, it would be incredibly faint. So the next important thing to talk about are what we call pulsars. So in 1967, there was a graduate student at Cambridge named Jocelyn Bell, and she noticed a really strange pattern in her data. So she had radio telescope data. So a telescope that was measuring radio wavelengths. And she saw a pattern. So, of course, the first thought was maybe it's aliens. Is this someone trying to communicate with us? Because it didn't make sense to see this spiking pattern. So she kept looking at it, and within a few weeks, she found 3 other very similar patterns, but at different locations and different timings of these peaks. So here she saw a peak, a peak, a peak, a peak, very consistent. What she called it was pulsing. So these objects she's realizing are pulsing. They are not showing the same light all of the time. They are very consistently pulsing on a specific timing, each object with different timing. So they called them pulsars, pulsing star. So they determined that the pulsar must be very small based on the data that they were looking at, because a regular sized star would be too large to pulse so quickly as they're noticing that pulsars do. So they know that these pulsing objects must be very, very small. And the pulses themselves only last about 1/100th of a second. Meaning it definitely has to be a very small object, because the pulse doesn't smear the data. Doesn't see any blur of the data. It's very clear, very short bursts of these pulsing. So if you look at an example, here I have Earth. Here I have a white dwarf with a radius of 6,000 kilometers. So if you look at the closest point on a white dwarf and the farthest point on a white dwarf in terms of from Earth's point of view, so here's Earth. So what we can see of this white dwarf is this part of the star that is closest to us. And then we can also see here the part that is furthest away from us. The difference being 6,000 kilometers. So if we saw a pulse, we would get the light or the radiation from the closest edge first. And then we would continue for however many seconds to receive the pulse from the furthest point away. So even a white dwarf, which is quite small, would smear or smudge the pulse of light. So it would look more like not a quick burst, but a longer increase in energy. So the way that they were able to conclusively say these pulsars must be tiny was because the pulses were so clear. They were not smeared, they weren't blurred at all by how you'd expect with an object that has a larger size. So here is a artist rendition GIF. So pulsing objects, they realize they have to be smaller than about 300 kilometers. They realized they must be neutron stars because they can spin up to 1,000 times per second. Remember, those neutron stars are spinning very, very quickly. So that is what is giving off these pulses, is the fact that the star is spinning so quickly and it is very, very small. So pulsars are thought to be an object that is emitting beams of light from two ends, similar to a lighthouse. So when those beams sweep over Earth, we see this pulse of light as this beam sweeps over us. So we detect this pulse. We see this increase in radiation. But we're only seeing the pulse if the beam happens to sweep over Earth. So there's other pulsars that their beams don't sweep towards Earth, so we don't detect anything with our telescopes when trying to observe them. So pulsars actually change with age. So at first they spin incredibly fast, But as the object loses energy, it begins to slow. So similarly to our sun, how our sun is losing energy slowly because of solar wind, pulsars have pulsar winds, radiating really slowly its energy out to space. So our oldest pulsar is about 10 million years old. And from Earth, the pulses will appear very, very strong when we have that beam passing directly over Earth. It's not always perfectly aligned, though. Some pulsars pass right over Earth, giving us a really strong pulse of radiation that we can observe. Some don't pass over Earth at all, so we have no way of looking at them. Some pass only a little bit over Earth, so we will actually see a sort of a mini pulse. So we know that it's a pulse, but recognizing that the intensity is rather low compared to one of the stronger pulses. So that must mean it's not perfectly aligned with Earth, but it's aligned enough that we can still see that pulse. So we know pulsars come from supernova. Do we find them in supernova remnants? Pulsars, we've determined we can detect them for 10 million years. So the oldest pulsar is about 10 million years old. Supernova remnants really only survive for 50,000 years. So most pulsars are actually not within supernova remnants. So most of the pulsars that we find or that we observe are no longer near supernova remnants. So some pulsars can move very, very quickly and leave the remnants of the supernova quite quickly. The supernova explosion, remember, it can kick other stars away. Sometimes supernovas will be in binary systems where there are two stars linked together in one of those binary systems. This can also fling other nearby stars away. So here we can see this star, 1996. I know this is old data, but we have 1996 here. And then just a few years later, we see 1999. It's in a different location. September of that year, it's in a different location, and it continues to move along this path. So this brings us a little bit to our binary system. So remember, the binary system is when there's two stars that are linked because they're orbiting around their center of mass. So you can think about the fact that they orbit each other, but we know that they're actually orbiting around the center of mass between them. So this can happen with neutron stars as well. So two neutron stars can orbit each other. And what we find is that becomes a binary pulsar system. So astronomers actually noticed that the pulse period can change over time, over about an 8-hour system, meaning over an 8-hour cycle. This means that they're looking at one of these binary systems. Each pulsar has a very consistent pulse that through time is going to be exactly the same. If they're seeing a change in the pulse period quickly over 8 hours, they must be looking at two different objects. So realizing that they're looking at a binary system. So then, of course, scientists can use the red shift versus blue shift to determine when the neutron star is moving away from Earth versus towards Earth, or neutron stars, and determine that it is, in fact, a binary system. So there can also be situations where there's a binary system with one neutron star. So one star has become a neutron star. The second star in the system is not yet dead. So the binary system is made up of a regular star and a neutron star. So what happens here is the regular star will constantly be losing mass because mass will flow from the star towards the neutron star. The neutron star is a tiny amount of matter. It's quite small, but it has a huge amount of energy. It has incredibly high temperatures. It's releasing X-ray and gamma ray. Remember, they're not usually visible in the visible wavelengths. They only produce X-ray and gamma rays. So this neutron star is just slowly sucking all of the matter and the material out of its companion regular star. It is slowly taking all of the matter from this star. What happens is the increase of matter to the neutron star will actually cause it to spin even faster and can increase the pulse period. It'll happen slowly. It's not going to be something that happens over the course of one of our days. But we can see an increase in pulse time, pulse period, because we see this neutron star is going to be gaining material. So here we have a bit of a diagram of our neutron star. Remember, they're quite small, they're very, very, very hot, and they have incredibly strong magnetic fields. And they also have, they send out beams of extra additional radiation, very strong, high wavelengths, very high energy, short wavelengths out of their two different directions. So there's always two beams of that additional radiation flowing out of the neutron star. So that is when a high mass star, after leaving the main sequence, becomes a red supergiant, explodes to a supernova, and when it is sort of that medium size, so it is a high mass star, but it's not an incredibly high mass star, it's going to become a neutron star, or what we call a pulsar. Very, very hot, very, very small, very strong magnetic field, and spinning very rapidly. So the next thing to think about is what we call escape velocity. So escape velocity is the speed on any object that is needed to escape the gravity of that object. So it depends on the mass of the object and also your distance from the center. So for Earth, here's the North Pole. Here's our Earth. If we were to try and shoot a cannon, or let's say it's not a cannon, but it is a satellite, into our orbit, there's a lot of math that has to be done to calculate exactly the speed that it needs to be launched so that it gets to the right height and will be able to orbit. So it'll be stuck in our gravity around Earth. If you do not launch the satellite fast enough, the object is going to fall back towards Earth. So that means it's not going to be caught in our orbit. It has not, we did not calculate well enough to get the object out of our gravity, meaning eventually it's going to fall back towards Earth. When we have escape velocity, is we're calculating the velocity that it's going to take to get an object completely cleared of our gravitational field. So how do we get this object, say it's a satellite, say it's a rocket ship, say it's people going to Mars, how do we get this object out of our gravitational field? So it really depends on the mass of the Earth and then the distance from the center of the Earth out to where your object is. So if an object has a very large mass and a very strong gravitational force, you need a very high velocity to escape. So to hit that escape velocity, you must be going very, very fast. If you're further from the center of mass of the object, you don't need quite as much velocity. So to leave from the surface of Earth, so if you are at sea level, your object that is trying to reach escape velocity, leave our gravitational field, must be traveling at 11.2 kilometers per second. But if you are launching from a tower that was 1,000 miles high, don't try and build one, that's really tall. Leaving a tower 1,000 miles high, so no longer at the surface, you're 1,000 miles up when you're launching your object, launching your rocket ship. the speed is different. So you only need to be going 10.4 kilometers per second to leave our gravitational field. So it's not only the mass of the object, but it's your distance from that center of mass. So are you at sea level? Are you up on this 1,000-mile high tower? Are you up on the top of a mountain? These things all make a difference in how you calculate escape velocity. So, a black hole. Imagine that you have an object that is big enough or small enough where the escape velocity is higher than the speed of light. So in order to escape the gravitational field of this object, your rocket ship must move faster than the speed of light. So our understanding of relativity says nothing travels faster than the speed of light. Nothing can travel faster than the speed of light, even photons themselves. So if escaping your gravitational field requires speeds faster than the speed of light, then nothing can travel that speed, meaning nothing could escape, even light. So this object would never be seen because no light can escape. Nothing can escape. There's no light. This is a black hole. So how does this work? If we have a collapsing star and it's greater than 3 solar masses in size, nothing can stop this collapse. So it's too big, too massive for degenerate electrons, which would cause a white dwarf, too massive for degenerate neutrons, which would cause our neutron star. So theoretically, this object would collapse to nothing. It would collapse to a radius of 0. But when we think of singularity, an object that's collapsing is going to increase in density and increase in gravitational force. If the object actually would collapse to a radius of 0, then the gravity of that object, the gravitational force, and the density of that object become infinite. If the object collapses to a radius of 0, both the gravity and the density become infinite. So a black hole is a star's core when it's contracting to the point where the escape velocity of the core of the star is higher than the speed of light. So the escape velocity is more than the speed of light, meaning nothing can ever escape this object because nothing can move faster than the speed of light, not even light. So no light can escape from a black hole. We cannot gather any information on these objects because everything that we know about space is from looking at light, different wavelengths, understanding the light that's being emitted by different objects. We can't do that because no light is being emitted. It emits no light at any wavelength. It emits nothing, these black holes. So here's where things get a little tricky. So Albert Einstein described space and time as one single entity. He called it space-time. And he said that gravity is just a curvature of the field of space-time. So a curve we see here in this diagram, in this drawing, I should say, of what this field, which we're calling space-time. So if enough matter is packed into a small volume, meaning that if it's dense enough, space-time can curve back in on itself, meaning this curve could dip so low that it actually circles back into itself. So objects can flow into the black hole, but they can never come out. Nothing can escape, not even light. So here's another drawing cartoon of the concept of this field of space-time, where the more dense an object is, the larger the object is, excuse me, it's going to cause a larger curve in this space-time field. So you notice think of it like a blanket or a sheet. If you put something small on it, it's going to make a little indent. Something larger, let's say it's double the size, double the weight. This one's a golf ball, this one's a basketball. It's going to put a little bit more of an indent into your sheet. If you put a bowling ball, this is going to put a huge indent into your sheet. So that's really what's happening with what we call this field of space-time, where the larger the object is, the more dense the object is, it's going to cause a larger curve in this field of space-time. So black holes have what we call an event horizon. So this is the boundary between the black hole and sort of the rest of the universe. What is considered the black hole versus what is no longer the black hole. This event horizon, the circle of the event horizon, outlines the area of space where nothing is going to be able to escape. So it outlines the area that would be the black hole. So the escape velocity within the event horizon is higher than the speed of light. Now the escape velocity of something outside is less than. So outside of the event horizon, you can see here, there's light. So we have observations, we can see light from outside of the event horizon. We can't see anything inside that event horizon. So what is a black hole? Is it a giant vacuum? No. So essentially, this is pretty accurate. It's not for time travel. I know there's a lot of movies, good and bad, about that concept, but it's not true. A black hole would crush you into very, very, very small space. That also is true. Is it a huge vacuum? No, definitely not. This is a really common misconception. So the black hole is not sucking everything in around it. It is not a vacuum. It does not work that way. What a black hole is really just a gravity field, and it's a really big one. So the star, remember, is huge. These are our largest stars that create a black hole. So these stars are going to create a curve in our field of space-time, depending on the size of the star, the gravity of the star. A black hole creates a huge curvature in this space-time field because remember, the star that creates a black hole are our largest stars in the whole universe. Only the largest stars create black holes because it requires a huge amount of mass to create this kind of curve in our field of space-time. So there's a huge gravitational force, yes, due to this object being so dense, but it's only right close to the black hole. So it's not a vacuum, sucking everything in slowly around it. We're not all slowly moving towards all the black holes. It doesn't work that way. It does have a very strong gravitational force, but only right here at the black hole, or at the center of what used to be the star. It is not sucking in things from across the universe. So it is not a vacuum, which is a very common misconception. Would you, if someone gave you a bunch of money, volunteer to jump into a black hole? I would not. Let's think about this. If you were 1 astronomical unit away from the black hole, which remember is the distance from the Earth to the sun, you would start to fall towards the black hole very slowly. And as you pick up speed, you would, as you fall and get closer to the black hole, you'd pick up speed. So as you're falling, you're increasing in speed as you go. You would reach, so you're 1 astronomical unit away, meaning you're the distance between the Earth and the sun. So if we pretend that the sun is a black hole, and you go to jump into it, jump off the Earth into the black hole, it would take you about 2 months to reach the event horizon. So for people watching you, let's say we figured out a way to observe this. Maybe Red Bull's worked with Tesla, put up some cameras in space. It would look to us on Earth watching you do this crazy thing that you were falling slower and slower and slower and slower. And you would not actually ever reach the event horizon to us. You would not be falling evenly. So your body would not be falling at the same rate, the same speed the whole time. If you jumped feet first, your feet would actually be pulled more strongly than your head because your feet are closer to the core of the black hole. So you would get stretched out. So you would also be crushed sideways, but you would be very stretched out. So what happens is then the friction of these two forces of being stretched and elongated while also being totally crushed sideways would heat up your body to millions of degrees before the point that you even reach the event horizon. And you would actually yourself emit X-rays and gamma rays. That is how hot your body would become. At this point, I don't know what we would call you. You would be like a really, really charred astronaut. But you would be emitting X-rays and gamma rays, which is pretty cool. So I don't advise. If you ever get this offer to jump into a black hole, I would say no. Definitely not. You're not going to make it. So I'm telling you, these black holes cannot emit light. We cannot see them. We can't observe them at all. How do we know that they exist if they're completely invisible? Because light cannot escape. What happens is, if matter is flowing towards the black hole, like you, for example, if you were to jump towards the black hole, it's going to spin inwards towards the black hole. So it's not going to fall just directly straight into the black hole. It's going to get caught in the rotation. So it will spin. This is not a picture. This is a drawing, a painting. The material is going to spin inwards around this black hole. So as it spins, as it gets closer to the black hole, it will actually heat up. And as it's heating, and before it reaches the event horizon, before it gets to the point where the escape velocity is so high that we wouldn't see anything anymore, it actually will emit X-rays. So the material falling into a black hole heats up so high that it will emit X-rays before it gets to the point that it reaches that event horizon. So if you have a single black hole by itself off in space, there's not that much material flowing in to use to measure. So we can really only see the black hole based on the material that's around it. However, if we have a black hole that's in a binary system, like this diagram here, like this drawing here, I should say. So this is a binary system with this star and our black hole. So it's constantly, just like the neutron stars do, constantly sucking material from this star, sucking matter in to the black hole because it's so close. Remember that gravitational field is quite strong. But it's only because this object is so close. So this black hole isn't taking material from anywhere else, only here, the companion star in its binary system. So we can actually look for binary systems that are producing X-rays because we know that material that's flowing from the companion star into the black hole is going to produce X-rays before it reaches the event horizon. So when we find binary systems that are producing X-rays, that are giving off X-rays, we know one of those objects must be a black hole to be able to heat that material to the point that it is producing those X-rays. So we can have both of these star deaths can be part of binary systems. So we can observe both a neutron star or a black hole if they are in a binary system. So really, what's the difference? If it's pulsing, it is a neutron star. It's a pulsar, it's a neutron star if it's pulsing. If it is larger than 3 solar masses, it cannot be a neutron star. So if it has a higher mass, it cannot be a neutron star. We know it must be a black hole. Are there observations of this? There was a study done of 12 X-ray binary systems. So there were 12 binary systems that were known to produce X-rays. And it was found that 6 of them were neutron stars, 6 of them were black holes. So it really depends on, is the material spiraling inward, producing those X-rays and then just disappearing? Then all of a sudden we don't see anything in the center. Or is the material spiraling inward and then we actually see the material hit the surface of the object with a burst of energy? So the big difference is, can we see anything happening in the center of this binary system or not? If we can't see anything in the middle, we know that it's a black hole, because at that point, nothing is being emitted. No wavelength can escape the escape velocity necessary in the black hole. Neutron star, however, will emit light. We'll see that energy burst at the sort of surface of that neutron star. So, some evidence: black holes emit jets of energy, really similar to the way that protostars would emit jets of energy, sort of at the top and bottom. And we have actually been able to see and observe this in the radio wavelength. So let's say this again is just a drawing, not a photograph. An accretion disk, so where all of this material is coming into the black hole. Here we have the event horizon showing the edge of where light can escape. Some of the material can be ejected from this disk out sort of the top and bottom, and we are able to see those in the radio wavelength. So another way that we can be certain that we are looking at a black hole. So there's also something called a hypernova and a hypernova explosion. So it's believed that stars that are 20 times larger than the sun, so 20 solar masses or larger, can collapse almost directly into a black hole. So after the star exhausts all of its fuel, it's so big that it collapses directly into a black hole. So the star is so large, it would spin so quickly as it is collapsing that the equator of the object would slow down and the poles would actually fall inward very quickly first. This would cause what we call a hypernova explosion. So it's really, really intense radiation and gas that would be ejected from the axis at both poles, so sort of at the north and the south of the star, because of this very quick collapse where the poles would fall inward as the equator is slowing down. So do we have photo evidence? So a couple years ago, the first photo of a black hole was published, which is quite cool. So we're not seeing the black hole. We're seeing evidence that a black hole is there based on what's around it. So you can't see the black hole, but we can see that event horizon. I mean, we know that the black hole is there. We see the event horizon. Really, we're seeing the outline of the black hole. So we see very, very hot glowing gas that's falling inwards. It's outlining the event horizon for us. So this took more than 10 years to get this image, and all of our radio telescopes. So a full global network of telescopes. Here is the article if you want to read more about how they actually captured this image. We're able to look at all of this material, this glowing material falling inwards towards what we know is a black hole. So we don't actually see the black hole itself. We see the lack of light, meaning this is the outline of our event horizon.